I think our brain is still alive and still our blood have some caffeine. Next speaker is Deepa Venkitesh. Deepa Venkitesh obtained her master's degree in physics from University of Kerala and PhD from IIT Bombay. She is currently a professor in Department of Electrical Engineering, IIT Madras. Her areas of research interest included coherent optical communication and photonic signal processing for analog and digital systems. She has published over 50 articles in international peer-reviewed journals and many more in conferences. I have one paragraph here. Okay, we will invite her for. Okay. She is a professor, so I am still a student. uh, she has published over 50 articles in international peer-reviewed journals and many more in conference. She has bestowed with the Young Faculty Recognition Award of IIT Madras in 2012 and the Abdul Kalam Technology Innovation Fellowship of INAE in 2021. She is senior member of OSA and is currently the associate editor of OSA journals Advances in Optics and Photonics and editorial board member of IET Optoelectronics. She is also currently the associate vice president of Women in Photonics of the IEEE Photonics Society. So I would like to invite her to present her talk.
This is going to be completely different from what we had in the morning. Let's get back to science. Okay. And the topic is actually slightly different from the themes that I saw in the conference, in the whole workshop. Pointer, forward, backward. Okay. We had lots of talks centered around quantum technologies and biological sciences in general. But this is completely different. We talked about, this will work? Okay. So we talked about how fast we can think. I'm going to talk about how fast we can communicate. When I say communicate, it's not the communication you talked about in the morning, it's about really sending data from one point to the other. Looking at the diversity of the audience, I went back and changed my talk completely yesterday, and I try to make it as tutorial as possible. I think the objective is not to describe my research, right? To just keep everyone aware of what's going on in the area of optical communication. Okay? I had an opportunity to write an invited article in Journal of Optics last year on something similar, slightly more technical than what I'm going to be talking about, but if people are bored of this, they can look up this article. It's come out recently, decent. So let's start by talking about the omnipresent optical communication. So if I ask you a question, let's say you are making a phone call from here to the US, how is your signal getting transported? 2 to 1. Oh. Fine. So, because we'll just stop wherever we are at that point. So, students, tell me how you're making a phone call from here to the US. How is your signal reaching the US? Let's try to call Anita when she goes back. Then you can ask me the question, am I making a mobile phone call or am I making a Google Meet call? Or am I making a phone call through the Google Meet? It doesn't matter what it is. Let's take the standard mobile phone call. How is that call happening? Anybody? From the phone, where is your signal going to? The tower. From the tower? Satellite. From the satellite? Receiver tower. And then it goes to the... Okay, I'm going to say something that phone calls like this do not happen anymore. Phone calls does not work that way at all. Up to the point where you reach the tower, it's fine. It doesn't go to the satellite, or rather only a very small fraction of the calls that you make go to the satellite. It's very expensive. You couldn't be paying a bill of 50 rupees if you're making use of the satellites, right? It's going through optical fiber. Okay, each one of your call, whether it's Google call or mobile call, everything is finding its way through an optical fiber. So how does a connection happen? In fact, you had the answer here, right? From your phone, it goes to the tower. From the tower, there is what is called as a front haul cellular network, which is of lengths less than a kilometer. There are these nodes which connects it to the metro links, Bangalore, Calcutta, Delhi, Bombay. India has multiple metro links, right? National Knowledge Network is one of the metro links. The distances are hundreds of kilometers there between the nodes. I'm talking about distances between these nodes. And then if you want to reach the US, this is not enough. It goes to the nearest submarine landing station, which could be from Bangalore. The nearest submarine station could be in Chennai or in Cochin, right? And then it would find its way through this, what is called the core network, which is the submarine network. There are fiber cables under the sea. There are at least 100,000 times the diameter of the earth. That length of fiber cable just under the sea, okay, which is making all these interconnections. And then it finds its way back. So Anita's core submarine drop point may be somewhere here, and then it finds its way back to the metro network, to the cellular network, and then to her phone. That's how a simple phone connection is working. Then talk about data centers, accessing the clouds. We are all sitting at home and fiber to the home. All this is interconnected through this invisible optical communication link, which you are not seeing, right? And now you think about it, you have learned about fiber optics in your class 10, and you know that it is a hair thin fiber which is taking all this connection, right? So today's talk is all going to be about that hair thin fiber, what you can do with that hair thin fiber for communication. For biology, there are lots of other things you can do with it, okay? So let's begin at the beginning. It can move only through this, okay. The word fiber optics was first used by an Indian gentleman, Narendra Singh Kapani, while he was working in the UK, but not in the context of communication, but in the context of using it for something we call today as endoscopy, right? And so he's still called, or rather he is honored with the title father of fiber optics. Even though in the strictest sense, the fiber optic communication was enabled by Charlie Cow's group in Corning in 2009, people were making optical fibers, were attempting optical fibers even before that, but this 4 dB per kilometer made it possible for transmission through reasonable distances, respectable distances, right? That's where this 4 dB per kilometer is important. And very soon, within a decade, by 1979, the NTT group demonstrated 0.2 dB per kilometer at 1550 nanometer. It's the loss in the fiber. So from 4 dB, we came to 0.2 dB very quickly. And to give you the perspective of that, we are struggling from 1979 until now. Even today, the state-of-the-art fiber has, we made a progress of 0.03 dB per kilometer over several years, simply because it's a material loss. It's silica, and silica has Rayleigh scattering. So the fundamental material loss you can't beat. You can beat it by using hollow core fibers. You don't have fiber at all. You can potentially bring the loss down because there is no material, right? But this is the state of the art. Now that we have the fiber to communicate, which is very low loss now, which means that you can transport information, you can modulate on light and transport information through very long distances. How do you, if you look at how technology evolved, it is how do you transport light? I mean, just like I'm doing this on and off and on and off, this is what is called as on-off keying. So the simplest thing anyone could think of how to communicate is, anyway, we are going to be talking about digital communication, which means all what we want to, even though all your information is in analog nature, you will convert that into digital zeros and ones, and then you transport your zeros and ones. And the receiver knows what does a zero mean and what a one means, and that gets converted into analog form. So you use analog to digital converters at the transmitter and digital to analog converters at the receiver. The simplest way of taking the digital information was what we call as the NRZ signaling, non-return to zero signaling. That's what I'm demonstrating here, on and off at a fixed rate through modulators. And in the constellation space, this is your Argand diagram, which is in phase quadrature or real imaginary. your two dots represents the two possibilities of your information, right? And this is how the first fiber optic link got demonstrated. And this is intensity modulation and just direct detection. A photodiode will tell you send a reverse current if it sees light, doesn't send a current if it doesn't see light, and that's very simple, right? So there was nothing drastic about the technology that was required to do this. Faster you signal, the faster you send the information, right? And at some point we wanted to transmit for longer distances. So in the 80s, people started looking at what the quantum optics group is very familiar with, this heterodyne receivers. So 80s communication people used these heterodyne receivers to improve the sensitivity. But soon that was not required, that technology became obsolete at that time simply because of this discovery. And we are really waiting for a Nobel Prize for the invention of erbium dope fiber amplifiers, because that has completely changed the way optical fibers work, right? Where in the optical domain you can amplify signals, and not only can you amplify, you can amplify multiple channels. So it's like a highway. You have multiple tracks, each track will be different colors of light. All these colors can be modulated independently and all of them can be amplified simultaneously. So you can transport a really large amount of information. How large? At some point we were stable, the technology was kind of, it plateaued at 10 gigabits per second. So you started signaling at 10 gigabits per second, 80 channels, this 80 dense WDM channels, 50 gigahertz spaced channels. This 80 number was restricted by the ability of the amplifier to amplify. The amplifier had a spectral gain bandwidth and it could amplify only up to 80 channels, right? But that was plenty because you had 800 gigabits per second that could be transported through a fiber. What is the internet speed that you get on the phones today? What does your speed test tell you? Megabits per second, and you are at 800 gigabits per second, right? Looked very plenty at that time. That was the year 1995, 2000. There was absolutely nothing that was required to be done, people thought, in the area of fiber optic communication, okay? Now, you said 800 gigabits per second, but as engineers, as technologists, as scientists, we would like to know what limits. Why only 800? Why? What puts a limit? Is there an ultimate capacity limit? And the ultimate capacity limit was actually derived in 1947 by Shannon, and the capacity in a linear channel, doesn't matter whether it's a fiber channel, free space channel, whatever it is, right? The moment you do digital communication, the capacity, which is the fastest bit rate that you can transport, is related through its bandwidth, because when you're turning on and off, remember your Fourier transform, on and off is a square signal. It has a sink shape in the spectrum. That sink, width of that sink is your occupied bandwidth. That has to be related to this, right? So this capacity and bandwidth is related through signal to noise ratio, right? So they define this quantity called as spectral efficiency. You have a spectrum with you. How much can you pack that spectrum? What's the fastest rate with which you can pack that spectrum? Bit rate divided by occupied bandwidth. That now suddenly becomes very simple. I plot this. This is signal to noise ratio on the x-axis. Spectral efficiency is the ability to pack, how much can you communicate, right? So it turns out that at the receiver, so the shaded part is the error-free transmission as predicted by Shannon. So if you, for example, have 5 dB SNR, you can pack spectral efficiency of, you can carry 2 bits per second in 1 hertz of frequency, right? What does that mean? Let's just do this calculation. 10 gigabits per second, right? We said 10 gigabits per second, 80 channels. So you multiply 50 gigahertz is the occupied bandwidth. It is 0.8 terabits per second in 4 terahertz of bandwidth. We are at a spectral efficiency of 0.2 bits per second per hertz. So what is the signal to noise ratio required for that? 0.2 is somewhere here. You can even operate at less than 0 dB SNR. What does it mean? It means that the optical fiber channel was so suboptimally used because at that time the requirement of data rate was very less. I was talking about 2005 where your smartphones were not still there, right? Internet had not picked up that much, right? So you're using the fiber so suboptimally, and we took things for granted that fiber is going to do everything for us, right? Now, do we really need this capacity, high capacity, right? So I'll give you now slightly futuristic picture, okay? Where is the capacity going to be required? People have heard of 5G auctions very recently, right? The 5G auctions recently, what happened, people, in fact, you would have also heard about the implementations of 5G. I would say the implementations currently that is happening for 5G is still not to the potential of what 5G can do. Essentially, the carrier frequency from 2.5 gigahertz in the current implementations, they made it to 3.5 gigahertz, that's all. But the real potential of 5G is in what is called as millimeter wave technology. Your antennas will start working at 26 gigahertz. Why would you want to work at 26 gigahertz? You will get really high bandwidth because your carrier frequency is 26 gigahertz, you can modulate it much faster, right? So, but then if you go to 26 gigahertz, your basic antenna theory would say that your beam diameter goes, it becomes highly directive. Then what do? You do what are called as multi-sectors antenna. So this is an antenna which is the standard configuration. It is a phased array antenna. You can sweep to cover, these are the beams that are covering different instruments. So you need to be transporting the data to, for example, there is a standard configuration, 3 sectors, 64 by 64, 64 antennas here, what they call as a MIMO configuration, multiple input, multiple output kind of configuration. You calculate what is the data rate that is required here. The antenna structures, the towers are going to look much different in 5G because you cannot have all the processing there. You have to do centralized processing and then you have to transport your information through fiber. What is the data rate you need to transport? 2.4 terabits per second between one antenna and one base station. So you imagine what is the requirement and capacity at the back end, from antenna to base station and or the base station is going to aggregate so many such calls, it's going into metro and metro is going to aggregate, it's going into the core and so on. So it's, in every truest sense, it's exponential, right? So we need to rethink how to do our modulation, how to make use of this fiber. So how do you improve your spectral efficiency? You need to pack much better. So one way to do that is to play with mathematics and say that instead of doing non-return to, this is return to 0, this is non-return to 0, you target your frequency first and say that I want a very packed spectrum. You find out what is the time domain that I need to achieve that frequency domain, do that shaping in the time domain, so that way you have achieved. So that's the pulse shaping trick that we can do. The next thing you can do is revisit modulation. Do you really need to do on-off keying, right? We know in 1980s, I told you we have found coherent receivers. The heterodyne receivers were made even in 1980s. So can we not revisit? Heterodyne receivers give you the ability to extract phase, right? So can you not do the modulation in phase, right? So you, instead of amplitude and phase, instead of modulating only in amplitude, which is here, the constellation, can you not use phase? And not just that, there's no need, nobody said that you can code, you need to send only one bit at a time, right? You can group bits, form symbols. So for instance, the simplest way of doing that is, let's say you group 0, 0 and you call that as a symbol A, group 0, 1, call that as B. Whenever 1, 0 appears, call as C, 1, 1 appears, you call as D, and instead of transporting bits, you transport symbols now, right? And if you're able to identify the symbols, then you know what is the bit that you transported, right? So here you needed so in one signaling, you are actually sending 2 bits of data. So you already improved the spectral efficiency by a factor of 2, right? And how do you do that? You can use 4 phase values. So you can say that I will transport 45 degrees, 135 degrees, minus 45 degrees, and minus 135 degrees. So you introduce phase, you give these measured phases for each symbol duration and transport them. And at the receiver, you kind of decipher these phase values. So this is what is called as a QPSK constellation, quadrature phase shift keying constellation, okay? There's no need to again stop at 2, you can now start grouping 4, A, B, C, D. So you will have 16 points in constellation, you can keep expanding. So this is 16 quadrature amplitude modulation, right? So how do you achieve this? You identify 16 levels of amplitude, 16 levels of, multiple different levels of phase. You can pack 4 bits, and this is the traditional 16 QAM constellation. Now you are in optics, the modulation is in optics, so you have one more degree of freedom, which is polarization. So you can do 16 QAM in one polarization, you can use, basically you're using this of the electromagnetic field. You can use 16 QAM in another polarization, so you increase the capacity by a factor of 2 more, right. So the whole pathway changed after 2005. What we started using is this QPSK. So tell me, what is a standard? I told you 10 gigabits per second was earlier. Today's standard is, can you take a guess? What is the standard of optical communication? It's no more 10. 10 does exist for shorter reach networks. It was 100 until a couple of years ago, 100 gigabits per second. It is now at 800 gigabits per second. Technology becomes progressively harder and harder to achieve that. But the point I'm trying to say is that there's a lot of now physics involved, because now you're trying to use polarization. See, you will use polarization, but is your polarization going to stay as is as it passes through the fiber? No, it's not. It's going to mix. So you need to know how the polarization is mixing, and you work out algorithms to demix. Do you think your fiber is completely flawless? It has dispersion. So what is the consequence of the dispersion? The pulse spreads. And so what you may have transported like this would finally appear like this, or even complete watch, right? So there's a lot of physics inspired signal processing you need to do, because you understand the physics of what goes on in a fiber. So you do that and get your data back, right? So there's a lot of work that still needs to be done to make these signal processing algorithms better. This is just to show you, this is the setup that we have in our lab. It's quite an expensive setup, so this is a appeal to the students. If you want to play with any of these modulation formats or do the signal processing, please feel free to write to me. We can make use of this setup to try out your ideas. Okay. Sorry, I'm going again. What limits? So now I showed you that I can keep increasing the modulation. I can do 16 QAM, I can do 64 QAM, I can do 256 QAM. Then what limits, right? Finally, your SNR, signal to noise ratio. So 16 QAM, this is 16 QAM, 64 QAM, this is 256 QAM, and so on, right? The problem as you keep going to higher constellation is that you should be able to identify each of those dots, which means your analog to digital converters should have enough vertical resolution to identify your different levels. But the problem is that as practical problems, okay, as the bandwidth in your analog to digital converters go on increasing, its ENOP, the effective number of bits, the vertical resolution it can give, starts falling. So which means you can't have high bandwidth and 256 QAM happening, right? There's a problem. So there are optical solutions. So I see here, this is one area of my work, photonic ADCs, right? Where can you do photonic front ends to solve this problem, right? Do photonic signal processing to improve the performance of electronic ADCs. I'm not going to talk about that now. Urvashi is going to stop me anyway now. So so that's the problem in scaling. In principle, in theory, you can keep increasing the constellations. Practically, you can't do it. The other problem in increasing this, is that increasing the reach. You don't want to travel to farther distances, right? As you keep increasing the span is the each span is 80 kilometer of fiber. So you keep increasing the span, the signal to noise ratio dropped, which means you modulated at this, which required a signal to noise ratio of 20 dB, but maybe at the receiver it's only 5 dB. Then all this cannot be retrieved. So that's a problem, right? So you can't, it seems like you can't transport high capacity for long distances, and we do want high capacity for long distances, right? So that's another problem. And the third problem is, you may say that, increase the power, right? What is the problem? You want only SNR, right? So noise is increasing, but you increase the signal power. We can make kilowatts and petawatts of laser. The problem is fiber is nonlinear, right? Beyond a certain point, as you keep increasing the power, the Shannon capacity limit actually drops. So people call it as nonlinear Shannon limit. Shannon may not have even imagined there is something called nonlinear Shannon limit, but this is what hits our limit, right? So there are multiple challenges here to reach high capacity. I'll stop at this slide, right? Where how as somebody who has background in physics can solve these problems, right? four-pronged approach. One is not, there's no physics, it's just mathematics. Play with the math, right? And try to do all kinds of pulse shaping, all kinds of funny, because today's technology, there is no limit to what pulse shapes you can achieve or what you can do in the electronics, right? Whatever you can do in MATLAB can be done through an FPGA or an electron. So play with the math, try to pack as much of spectrum as possible, right? And that's smart choices. So people have done probabilistic shaping, constellation shaping. You know, why should this constellation look square? Why can't it be circle? Why can't it be a funny shape? Why can't, there are machine learning, you know, you throw in machine learning to it. You say depending on the channel, you decide what should be the way the constellation should look like, right? So that's one area for people who are interested in the maths and signal processing. The other one is you are limited, this has nothing to do with Shannon limit. You are limited by 80 channels because you are using EDFA. So I glorified EDFA in the beginning, but I am now saying that look, EDFA is putting you a challenge, right? You can do only 80 channels because you are using an EDFA. So use semiconductor, revisit semiconductor optical amplifiers. So that's another area we are working on to make what is called as ultra wideband, right? Replace the amplifiers with broadband amplifiers, parametric amplifiers, nonlinear amplifiers, but it has to be made energy efficient, right? So use that instead of EDFA. Then you don't have to do any of it. Third is scale the Shannon limit. Again, please take it with a bit of caution. I'm not saying that Shannon limit can be scaled. I'm just saying that increase the number of pathways. Use multi-core fiber, you use few mode fiber. In the same fiber, you try to choose multiple paths, right? So you scale it as instead of you saw that capacity is equal to bandwidth times log SNR, you say n times bandwidth times log SNR. You have 5 cores, you can increase the capacity as much. It comes with its own challenges, but this is again another area of our work we have demonstrated with few moded fiber. Right? And the fourth, which is my favorite, is throw in photonic processing. Wherever there is limitation in noise, which is contributed by electronic noise, you throw in photonic processing. Starting from photonic analog to digital converters, to what is called as optical phase conjugators, through phase sensitive amplifiers, right? All these are our different areas of work, but all that will help us solve the problem of future, which is a real problem we need to solve. Otherwise, our communication networks are not going to work unless we do something today to do the capacity scale. So let me stop here. I had some illustrations of photonic processing, but that's for another time. Let's get to this last part here. There's lot of learning. I came completely from a physics background and I'm now talking only the language of communication in many places, and that has been possible through my learnings through my collaborators. So again, I said this yesterday, one of the things that as researchers you should, I mean, you don't know everything when you start, and never be shy to ask people, never attempt to hide your ignorance. All of us are always learning, and it's better that it's good that we are learning. It's better to learn it in these kind of interdisciplinary areas than you say, oh yeah, I can put that idea here, right? Kind of thing, right? So the reason I'm saying this is because all my first work with communication started with my collaboration in Dublin City University, and I learned coherent communication through those experiments. And of course, the collaboration strength is very strong. And thanks to all the funding agencies who have trusted us in doing some of these things. And these are students over the years who have contributed to all the work that we are doing in the lab. Thank you.
I want to thank you again. So I will take 1 or 2 questions right now.
You can use circular polarization. Or any 2 orthogonal polarizations is fine. So you'll get a multiplicity factor of 2. You could do circular, you could do linear. Structured light is again giving you another order of multiplicity. And people have demonstrated increasing capacities with structured light in free space communication especially. I'm talking only about fiber communication. In the fiber communication, you need to modify your fiber. You need to have standard single mode fibers won't support your structured light, right? So people have used, demonstrated what are called as ring core fibers, which can support the OAM beams. So it will require a complete redo of the fiber.
If no student is asking, I can ask one question. Okay, so that is from the metamaterials perspective. So can you please comment on the negative dispersion engineering that is coming for 5G and 6G domain?
Okay, I have very limited knowledge in this, but are you talking about the intelligent reflecting surfaces? So I am not an expert in this area, but what I am learning right now is that you could paint surfaces with metamaterials which will reflect the beam in a desired direction to improve the improve the reach of your communication. Yes, people are talking about optical fiber made of metamaterials, just hollow core fiber, because one of the challenges in, I don't know if you've been following this stock market scam that recently one of the prominent females got arrested is in the, right? So the problem was this, the server was kept in the stock BSE or NSE, and certain companies got the server in the NSE, and certain other traders had the server wherever they are. You would think, how does it matter, right? Now, when those servers which are inside the NSE, the latency is 1 microsecond, let's say, and for the servers outside, the latency is 100 microseconds, because there is a fiber and it takes time for the light, even at 3 into 10 power 8 or 2 into 10 power 8 meters per second, it still takes that much time too, right? And so what happened is, certain preferred traders got early access, 100 microsecond early access to information, and they could gain. And that was the whole case about. So what is currently the data center networks especially, right? You're trying to reach your data center, your YouTube, you are very irritated when there is a delay, right? So where is the time taken? It is to reach the right server, right location. So people are now trying to use hollow core fiber, so that the core of the fiber is hollow, it's air. So from 2 into 10 power 8, you can reach 3 into 10 power 8 meter per second, right? And that, I think, is will definitely become very popular, because of there's a lot of economic impact of doing that, right? All this technology is definitely driven by economy, we know that, right? So silica.
Don't you think it's too far?
So long as it makes business sense, it's never too far.
Okay.
Right? The technology works that way, right? They don't, so long as you can make it and show that there is improvement, in terms of more data rate and in terms of lower cost.
Okay.
If you're able to do that, it's fine.
Sorry, maybe I'll discuss with you over the lunch.
Sure.